Okay, so you're someone who likes to get right to the point, right? And understand complex stuff without all the extra noise. Well, you've probably heard about this idea of messing with sunlight to fight climate change.
Yeah.
It's called solar radiation management, or SRM.
Yeah.
And yeah, it sounds kind of sci-fi, but it's actually a really big deal in science right now.
Oh, yeah, it's getting serious attention.
And today we're going deep on a really interesting part of this whole debate. It could change how we think about SRM completely.
Yep, definitely a game changer.
So to set the stage quickly, when people talk about SRM, they usually focus on two main things.
Stratospheric Aerosol injection, or SAI.
Right.
Ring cloud brightening, MCB.
MCB, yeah.
SAI is all about putting tiny particles way up high in the atmosphere to bounce sunlight back to space. And MCB is about making low clouds over the ocean brighter so they reflect more sunlight too.
Okay, so both basically ways to reflect more sunlight away from Earth.
Exactly. The idea is that these would buy us time while we work on the real solution, cutting emissions.
Right, not a replacement, just a temporary fix.
Right.
Okay, but this deep dive isn't just another SRM explainer. We've got some exciting new research for you, and it's about a side effect of SAI that might be way more important than anyone realized.
Yeah, this is big.
It's called diffusion brightening. And what it means is when you put those aerosols up high to reflect sunlight, it also causes the sunlight that does get through to scatter in all sorts of directions.
Right. It's not just blocking sunlight, it's changing how the remaining sunlight travels too.
And the crazy part is that this scattered or diffused sunlight ends up hitting the clouds below at different angles. And get this, it can actually make those clouds brighter.
Yeah. And brighter clouds reflect more sunlight back into space.
Yeah.
So like SAI has this extra boost that we didn't fully appreciate before.
Okay, so before we get into the details, why is any of this even important? We've talked about climate change a lot, and
Right.
Yeah, the Paris Agreement set some big goals, but the truth is we're not sure if the current plans to cut emissions are going to be enough.
Definitely not on track yet.
And that's a big reason why people are starting to seriously consider things like SRM.
Right. It's a recognition that getting off fossil fuels is really hard. And we might need something extra to avoid the worst of climate change.
Okay, so let's make sure we're all on the same page here. SAI is basically like creating sort of shield high up to reflect some sunlight away. And MCB is like giving those low ocean clouds a reflectivity upgrade.
Exactly. And in the past, most research has looked at these as separate things. Like, okay, what happens if we just do SAI? What happens if we just do MCB?
Right.
But this new research is different. It's about how those two things actually interact. It's about how putting aerosols in the stratosphere changes the very nature of the sunlight reaching those clouds below.
Okay, so back to diffusion brightening. So those aerosols high up, they make the sunlight scatter, right? So instead of a beam of light going straight down, it's more like
a bunch of billiard balls bouncing around.
Exactly. So the sunlight below the aerosols is coming from all these different directions.
Right. It's like it gets spread out or diffused.
Okay, and then this diffused light hits the clouds. But why does that matter?
Well, the angle of the sunlight hitting the clouds actually changes how the clouds interact with it.
Like if you shine a flashlight straight at something versus at an angle?
Yeah, exactly. To understand why, though, the researchers started with a simplified cloud. It's a theoretical cloud that's infinitely wide and deep, and it doesn't absorb any light at all. Now, obviously, real clouds aren't like that, but this helps scientists isolate how the angle of sunlight affects things.
Okay, so even though it's a perfect reflector, the journey of the light inside the cloud changes depending on the angle.
Yes, and here's where real clouds come in. They're not infinite, right? They have a bottom. So if sunlight enters at a steeper angle because it's been scattered by those aerosols, it has a harder time going all the way through and escaping.
Especially over the ocean, which is dark and absorbs a lot of light.
Right. So instead, the light is more likely to bounce around inside the cloud and get reflected back up to space.
So the cloud becomes a better reflector because the light's hitting it at a different angle.
Exactly. That's the diffusion brightening effect.
It's like a little trick of physics.
And what's amazing is that this idea was kind of hidden in plain sight. Like, we knew about how light and matter interact, but no one really applied it to SRM and clouds before.
The study even says this wasn't mentioned in a recent review of SAI impacts. That's kind of crazy, right?
Yeah, it's overlooked.
Yeah.
It's a great example of how even well-known science can have surprising applications.
Okay, so how did they actually show that this diffusion brightening is real? Did they do experiments in the real world?
Well, you can't really control the whole atmosphere for an experiment like that.
Right.
So they used a computer simulation. They focused on low-altitude clouds over the ocean near the equator, because that's where the sun's strongest.
Makes sense.
They used a tool called SBDART. which is basically a way to simulate how light travels through the atmosphere. And they added a layer of stratospheric aerosols to mimic SAI.
Okay, so they built a little virtual world.
Yeah. And in the first version, they used a lot of aerosols just to make the effect super clear.
So what happened?
Well, first thing, the sunlight hitting the cloud changed drastically. Without the aerosols, it was mostly just a direct beam from the sun. But with the aerosols, that beam got scattered all over the place. So at the top of the cloud, the amount of diffuse light increased a ton.
So the aerosols were like a giant diffuser.
Yeah. And that diffuse light was coming from a wider range of angles, just like we talked about.
And then what about the cloud itself? Did it reflect more sunlight?
Yep. The simulation showed that the cloud's albedo or reflectivity went up by about 9%.
Wow, 9% just from changing the angle of the light. That's huge.
It's a significant difference. But there's a twist. In that first simulation with a lot of aerosols, the total amount of upward radiation actually went down.
Great, really? I thought we were trying to reflect more sunlight away.
Right. So it turns out the type of aerosol they used in that first run actually absorbs a little bit of sunlight.
Ah, so while the cloud was reflecting more, the aerosols themselves were absorbing some too.
Exactly. So the net effect was less upward radiation in that particular scenario.
Okay, so what does that tell us about what kind of aerosols we'd want to use for SAI if we were going to do it?
It means the ideal aerosol would be one that scatters light really well, but doesn't absorb much at all. Because even a little bit of absorption can cancel out some of the brightening we get from the clouds.
So it's not enough for the aerosols to be reflective. They have to be the right kind of reflective.
Exactly. It's a really important detail for anyone thinking about actually doing SAI.
Okay, so to figure out how much of the effect is from the aerosols themselves versus the clouds,
Right.
they had to run another simulation, right?
Right. This time they used perfectly scattering aerosols. So these aerosols would reflect all the sunlight and not absorb any.
Okay, so now they can isolate the diffusion brightening.
Exactly. And what they found was really interesting. For thin cloud, the direct reflection from the aerosols is the main thing. But for thicker clouds...
And we're talking about a lot of clouds, right?
Yeah, a wide range of cloud types that are really common.
Okay.
For those clouds, the diffusion brightening effect was actually stronger than the direct reflection from the aerosols.
So it's not just about having that reflective layer up high. It's about how that layer changes the light reaching the clouds below.
It's this extra layer of complexity that we're just starting to understand.
Did they also look at how things like the amount of aerosol or the thickness of the cloud affect this brightening?
Yeah, they did a whole bunch of simulations to test different conditions.
Cool.
They found that more aerosols generally means more brightening, which makes sense because more aerosols scatter more light.
Right.
And the relationship was pretty linear, which means even a small amount of aerosol could have a noticeable effect.
Okay, what about cloud thickness?
For thinner clouds, the brightening effect was stronger because in a thick cloud, there's already so much scattering happening inside that the angle of the incoming light matters less.
So it's like the thicker the cloud, the less of a difference the diffusion makes.
Exactly. And they found that there's a sort of sweet spot where the diffusion brightening is most effective.
Yeah.
It's for clouds that aren't too thin, but not too thick either.
Makes sense. And what about the angle of the sun? Does that matter?
It does. The brightening effect was strongest when the sun was high in the sky. Like at noon when the sun's directly overhead.
Okay.
But when the sun's lower in the sky, like near sunrise or sunset, the diffusion can actually make clouds a little darker in some cases.
Interesting. So there are some situations where it doesn't work as well.
Right. But the thing is, most of the sun's energy reaches Earth when the sun's high in the sky. And the important cloud regions for this effect also tend to have the sun higher up. So overall, the global impact is likely to be brightening.
Okay, so some local variations, but the big picture is brighter clouds.
Exactly. And the researchers also pointed out that the big global climate models probably already account for this diffusion brightening in a way.
Right. Even if they weren't explicitly looking for it.
Right. It's probably baked into their calculations.
Yeah.
But this study gives us a much clearer understanding of why those models show what they show. It's like we've uncovered a hidden mechanism.
So it's not that they were wrong before, it's that we now have a better explanation for what's going on.
Exactly. And that better understanding is super important for making informed decisions about SRM if we ever decide to go down that road.
This also raises some interesting possibilities, right? Like, what if we intentionally put aerosols above clouds, even in the lower atmosphere?
Yeah, that's a fascinating idea. It could be a way to brighten clouds remotely without having to inject stuff directly into them, like with MCB.
So it's like a different approach to MCB.
Exactly. It might be simpler and have fewer unintended consequences.
And in some cases, maybe you'd get both effects, right? First, the diffusion brightening from the aerosols above, and then later some of those aerosols mix into the cloud, and you get the traditional MCB effect too.
Yeah, that's a plausible scenario. The study also found that SAI can change how much sunlight gets absorbed within the cloud, which is another thing we need to study more.
So lots more research to do.
Absolutely.
All right.
But from a practical perspective, if we were to do SAI, this study suggests that we should be thinking about how well the aerosols scatter light, not just how reflective they are overall.
Because if this diffusion brightening is a big part of how SAI works, then you want aerosols that are really good at diffusing.
Exactly. It changes the design criteria.
It also seems like if we got really good at MCB, like if we could make clouds super bright by injecting particles into them, then the extra benefit from SAI might be less.
That's probably true. If the clouds are already reflecting almost all the sunlight, then changing the angle of the incoming light won't do as much.
So the two approaches could kind of compete with each other in a way.
Yeah, it's a complex system with lots of interactions to consider.
So to sum it all up, this research has really shown us how connected SAI and clouds are. They're not separate. They influence each other in this really important way.
And that influence is a lot bigger than we thought. It's not just about the direct reflection from the aerosols, it's also about this diffusion brightening effect.
And that effect might be even more important than the direct reflection for a lot of common clouds.
It's a game changer for how we think about SAI. And it highlights how much we still have to learn about these climate interventions before we even think about using them.
Okay, so here's a final thought for you to chew on. Given this new understanding of how SAI and clouds work, how should we be approaching research and maybe even implementation of these technologies? Should we be focusing on making aerosols that are super good at diffusing light? Or should we be trying to figure out how to use both stratospheric and tropospheric interventions together to get the best results? Lots to think about.
Yeah, it's a really exciting area of research with huge implications for the future.
Thanks for joining us on this deep dive. We encourage you to check out the research we talked about and keep learning about this crucial and rapidly developing field.
Absolutely. It's a topic that deserves more attention.
And that's it for this episode. We'll see you next time.
See you later.